Hello.
Other questions? How the
killing vector is related to the symmetries.
Oh, killing vector related to the symmetries. Yeah. So the point is that symmetry transformation means the G prime mu nu of x is equal to G mu nu of x. Right? This is the condition. Okay. On the other hand, we know how to calculate G prime mu nu. Right? Then G prime mu nu of x prime is okay. So the idea is that we want to try to see how to solve this, and we want to do it for infinitesimal transformations. Okay. So we take x rho equal to x prime rho plus epsilon times I rho. Okay, some vector which you can take to a function of x prime or x, doesn't matter because it's already of order epsilon here. Okay. And then you just substitute in this equation. Okay. So using this, we calculate G prime mu nu. G prime mu nu of x prime. Okay. So this is given in terms of G mu nu of x. Because what appears on the right hand side is G mu nu of x, right? Or G rho sigma of x. In general, it will involve all components. On the other hand, we have to compare it with so G prime mu nu x prime, but we know we need G prime mu nu of x, right? So this now we write as G prime mu nu of x. X prime is x minus epsilon xi rho, so minus epsilon xi rho right. So here you can replace the G prime mu nu by G mu nu because it's already of order epsilon, so the difference is small. And then we just compare this. So we need G prime mu nu of x equal to G mu nu of x, right? So the required equation is G prime mu nu of x equal to G mu nu of x, right? Because that's the meaning of isometry. Okay. And then you just compare the two sides. Right? You have calculated G prime mu nu of x explicitly. Right? This is just from general coordinate transformation, and you are now demanding that this should be equal to G mu nu of x. Right? So compare the two, you will get some condition on xi. Okay. And that condition is epsilon times right. So this is what is the definition of a killing vector. Right. So what we see here is that if we have a continuous isometry, right, the infinitesimal version of those continuous isometry will give rise to a killing vector. Right? And the reverse is also true. Given a vector which satisfies this, right, you can generate a you can show that this is an isometry, right, infinitesimal isometry. So that's the relation between the killing vectors and isometries. Is this point clear?
What kind of transformation we are making that will correspond to different conservation?
Yeah, so here I have not talked about conservation laws, right? It is just a question of symmetry. That if the metric under a general coordinate transformation has this feature that G prime mu nu of x is equal to G mu nu of x, then we call this an isometry. that may or may not lead to conservation loss. That's a different issue. Right? Here you are just talking about the symmetry of the metric. No, see, preserving distance, general coordinate transformation preserves distance. Right? Any general coordinate transformation will preserve distance. Right? Isometry tells us that there is a transformation, right, under which the new metric looks like the old metric. Right? There may be spaces with no isometry at all. Right? Imagine a surface of a two-dimensional surface, complicated two-dimensional surface. Right? You take a sphere and crumple it. Right? That surface has no isometry. But the surface of a sphere has SO3 isometry, because if you make an SO3 rotation, okay, the metric looks the same. You will not be able to distinguish a point here from a point there, right? Because the metric around those 2 points are the same. Right? It's not manifestly visible necessarily on the coordinate system that you use. Right? If you take, for example, d theta square plus sine square theta d phi square, right? The only isometry that is visible is a phi translation. Rotation about z axis is a clear isometry, right? But it also has isometries under the x and y, rotation around the x axis and y axis, right? Which correspond to complicated transformation in from theta and phi. But those are also isometries, right? You know from intuition that these are isometries, because if you make such a transformation, right, the sphere looks the same. Right? You can also see it by using the embedding coordinate, right? Sphere, you can describe this again, we will see today, as two-dimensional sphere is the surface, right? And the metric is basically induced from the original Euclidean metric, right? But you just put this constant, so you get this d theta square plus sine square theta d phi square. But from this perspective, you can see that if we take x, y, z and make an SO3 rotation, right? This condition is the same, remains the same. The metric also remains the same, right? So when you think of it this way, it's clear that an SO3 transformation is an isometry, right? Even though it's not visible in the intrinsic coordinate system, right? When you write it as d theta square plus sine square theta d phi square. But if you want to give an intrinsic definition of isometry, it is this, right? The particular coordinate transformation, right? The new metric should look like the same old metric, right? And that should be distinguished from this, because this is a general coordinate transformation. But G prime mu nu may have a completely different functional form compared to G mu nu.
But why consider only this kind of pressure? So, for example, another thing that G prime of x prime is equal to G, that equal in value.
But that means that that is not the functional form doesn't remain the same, right?
I'm just asking why.
Because this tells us that if 2 points x and x prime are related by an isometry, right? Then by looking at the metric around x and metric around x prime, you will not be able to distinguish. The environment will look exactly the same. Take 2 points on the sphere, right? By looking at the local metric, right, you will not know that whether you are here or there, right? And that requires that there is a coordinate transformation that makes the functional form of the metric around this point exactly the same as the functional form of the metric around that point. Then it will not work, right? If they are equal in value but not in functional form, right, then these 2 points are not equivalent. Right? So we really need the functional form of the metric to look the same, right? So which means that if you have a point x1, right, you have some functional form of the metric. Around the point x2, right, the metric looks different. In general, suppose you take d theta square by sine square theta d phi square, right? If you take theta phi and theta naught phi naught, right, and try to expand the metric around theta phi and theta naught phi naught, sorry, theta 1 phi 1 and theta 2 phi. In general, the metric will look different, right? The Taylor series expansions will be different. But the fact that there is a coordinate transformation, right, that makes the functional form of the metric around one point the same as the functional form of the metric around that other point, means that these 2 points are actually equivalent. Right? The metric around them look the same. Is that okay? Right? So this is important that the functional form of the matrix should look the same.
When it comes to the case of cosmology, we are saying this average is a large distance.
Yes.
In this large distance, what is the scale we are talking?
Well, basically hundreds of light years, because certainly it's not at the solar system scale, right? I mean, our nearest galaxy which is not bound to Milky Way, is about 5 million light years away, right? So even in that distance scale, right, it's not uniform, right? We have a galaxy here and 5 million light years away, there's another galaxy, right? So you have to average over at least hundreds of millions of light years. But it's still, that distance is still small compared to the size of the universe, right? The visible universe, for example, today is about 45 billion light years in radius, right? So if you have to average over 100 million light years, you still have a lot of such regions, right? And it's the uniformity is over that scale.
When we say about this uniformity, are we taking all these kind of values as well as not any kind of matter?
Yes, indeed. So all matter fields, right, are separately uniform. And the point is, okay, you can ask why is it uniform, right? In fact, when people first wrote down the models of cosmology, they just took it as a simplifying assumption, right? They didn't know how to measure densities over such large scales. Okay? But now we know that this assumption is valid, right? And we will see there is an explanation for this based on inflation, right? Very early universe cosmology, which you may study near the very end of the course. Right? Why is the universe uniform? Right now, we are just assuming that it's uniform and trying to study its consequences.
So this is like separately uniform in all kinds of radiation.
Yes, indeed. So the matter density is uniform. Radiation is uniform clearly, right? Because the cosmic microwave background radiation is very uniform, right? And the cosmological constant is a constant, so that's obviously uniform, right? So it's the matter density which is the relevant quantity, and the metric is uniform, right? The metric satisfies this kind of relation.
When we define all these kind of things with respect to CMB also, even though very small, it also has some anisotropies.
Exactly. Yeah. So we are just ignoring that, right? At the scale that we are working on now, right? CMB we just think of as a uniform. Right? Basically, there's a 1 in 10 to the 5 fluctuation in CMB, right? But we are not working at that level.
And based on the time scale, are we interested from starting of the CMB the time forward? Or like, say, for example, if I wanted to know some information for CMB,
we'll see what we can do, right? I mean, we would like to know the information till the beginning of the universe, right? Wherever that may be, right? If the universe has been living for infinite amount of time, we'll like to get information about that as well, right? But we will see, according to our current understanding, the universe has a finite lifetime, right? And I mean, we basically want to study that whole span. Okay, but right now we only have to start from near what we know, right? What we know today. Only then by extrapolating it backwards, you may be able to get some information about the early universe. Okay, so what we said last time is that the universe has a cosmic time. And that a fixed time slice that means if we fix the value of t, let me call this cosmic time t. So a fixed time slice is homogeneous and isotropic. When averaged over large scales. Okay. So the first thing we will try to do is to understand what it means. Okay, what one means by saying that it's homogeneous and isotropic. Now, there are some metric I can write down, right, which if you look at it, you will know that it's homogeneous and isotropic. Okay, and I'll give an example, but what you want to know is the most general metric that satisfies this criteria, right? And for that, you have to first formulate what this means. Okay. So here is an example, right, which I think you will agree that it's homogeneous and isotropic, and that is dA squared. So if we take a fixed time slice, say t equal to some constant, right? The spatial direction is some constant times dx square plus dy square plus dz square. That's flat space. Right? Flat space obviously is homogeneous and isotropic, right? Flat space you just translate, right? It's clearly nothing changes, right? And if you rotate around any point, right? Again, that's a symmetry or the metric. Right? So flat space. So this is clearly an example of a homogeneous and isotropic space. But what you are asking is, what is the most general homogeneous and isotropic space, or homogeneous and isotropic space time? Okay, but when I talk about homogeneous and isotropic space time, you have to think the criteria is on a fixed time slice, right? And we'll try to make this more specific. So before we give the definition of homogeneity and isotropic, okay, we'll try to write down the most general metric and try to simplify it just by using coordinate transformation. Because as you have seen, that coordinate transformations do not change the isometry, right? It may change the form of the isometry, but if the metric had certain isometry to begin with, in the new coordinate system, the metric will still have the same isometry. Right? You have to basically conjugate by that particular coordinate transformation. So we are allowed to choose our coordinate system at will, and we'll also choose our coordinate system in such a way that the time coordinate is not transformed, so that fixed cosmic time here will mean fixed cosmic time, fixed time in the new coordinate system, right? Because that's what you want to use. So time coordinate will not touch. We'll try to see what we can do, how much we can simplify this form of the metric using the space coordinate transformation. Well, it's a covariant means what? Yes. We'll just take t prime equal to t, right? Then constant t slice is the same as constant t prime slice, right? Then we know that if the original time was the cosmic time, then a new time is also the cosmic time, right? So it is not, I mean, whatever manipulation you are doing now is not fully covariant, because you have given a special treatment to the time coordinate, right? You could write it in a fully covariant form, because given this, you can of course make an arbitrary coordinate change, right? And you can describe the universe in that coordinate system, right? Which will still have the same isometries, except that the isometries will look more complicated, right? If you mix up cosmic time with space. So for that reason, we will assume that there is a cosmic time, and we are not going to touch that coordinate, right? At least for now. So we start with a general metric. This is certainly the most general metric. Yes. Yeah, see, when you do a coordinate transformation, the way the isometry acts on the coordinates will be different, but the number of isometries will remain the same, right? Because given any isometry, in the new coordinate, we can write a corresponding isometry, right? So number of isometries is not going to change, right? But we want to keep the notion of cosmic time fixed, because what we are asking for that at fixed cosmic time, there is an isometry in the spatial direction, right? So if we don't want to mess up that concept, right, we have to work at fixed cosmic time, right? But we could have made an arbitrary coordinate transformation. It will not change the isometry, number of isometries, right? Because general coordinate invariance is symmetry of Einstein's equation, right? It's just that in some coordinate system, equations may be simpler, right? I mean, one example is the Schwarzschild metric, right? We got the Schwarzschild metric in this spherically symmetric coordinate system. But in principle, once you have gotten that, you can make an arbitrary coordinate transformation and write the metric. It will have the same physics, right? It's just that it will be hard to find a solution in an arbitrary coordinate system, right? So here is the same philosophy. We are assuming that there is a preferred time, right, such that at fixed time there is a homogeneity and isotropy, and you are going to use that, right? And that's the reason why when you make a coordinate transformation, we are not going to mix up that time, because then we lose that insight. Is it clear? Are there questions? No, that would be this case. Yeah, but there will be more general. We will write down the precise notion of what we mean by homogeneous and isotropic. Right? See, this is an example. This will come out as one of the solutions, right? But we will have to first give a precise mathematical definition of what we mean by homogeneity and isotropy, right? Which I have not done yet, right? It's just something in the air that intuitively you understand what it means, right? But we have not written a formula for this, right? What exactly is what we want, right? We'll write down the formula soon, right? But right now, all we are saying is that we will not go to, we'll leave aside this question of homogeneity and isotropy, which will impose eventually, okay? But now we just want to simplify this metric using a coordinate transformation, okay? Arbitrary coordinate transformation, but that coordinate transformation we want to restrict to a class so that t is not touched, right? Because suppose we define t primes to be a function of x and t, right? Then constant t will correspond to not correspond to constant t prime, right? So the slice itself, what slice is homogeneous, right? That notion itself gets changed, right? So then it will be much more difficult to implement this notion of homogeneity and isotropy, right? So in order to maintain the notion of constant time slice, right, we take t prime equal to t for now. Is this clear? Right? So you make a coordinate transformation. T equal to t prime, and x I is equal to, let me call this phi I of t and x. Okay. T of x, sorry, t. Let me write t prime x prime. T prime is the same as t, right? But I have written in terms of prime coordinate and x prime. And what you are going to do is to adjust this phi I is up to us to choose, right? I can make any coordinate transformation that I like. We are going to try to adjust this phi I to get rid of this term, the cross term. Okay. Now, the fact that it may be possible is here because there are three functions here, right? That you can play with. I runs from 1 to 3. And there are three functions here. Right? So you might hope that by adjusting these three functions, you may be able to remove these three functions, right? Just set this in the transform coordinate, just set this to 0. Okay, and that's what we'll try to argue that it is possible to do this. Just to simplify the form of the metric, right? Yeah, I mean, it's not necessary, but to simplify the form of the metric, we just want to set it equal to 0. So let me emphasize again that at this stage you are not imposing any homogeneity and isotropic constant. Right? All you are saying is that you have some insight that T is somewhat special, and you want to maintain that speciality. That's why here we are saying. Okay, but otherwise this is a completely general metric. Okay, and this for this step that I'm going to do now, you could have done it for an arbitrary metric. Right? It didn't have to be cosmological space time. Okay, so if we now substitute this here, then ds square becomes minus f1t x dt prime square. Okay, this t and x of course have to be rewritten in terms of t prime and x prime, but that we can do. Then the second term becomes f2i dx, and then dt becomes dt prime, and the dxi becomes del phi I del x prime j dx prime j. Yes, plus del phi I del t prime and dt prime. Is this clear? And the third term basically you have to square this. Right? This is what dxi has become. Right? So you have two factors of this. Okay, so let me just write this and then I think it will become clear. One will be let me change this to k. So we make our life a little easier. Then we have the cross terms. When you square this, you have the two cross terms. Okay. But those two cross terms give identical contribution because F3 is symmetric under I and j. Okay, so I'll just multiply it by 2. So that cross term will be 2 and then one more term which is the square plus right. So our goal is to get rid of the dt prime dx k prime term. So let's see where we get this is one term and this is another term, right? So we'll choose or try to choose. We have not said that it's possible yet. Try to choose phi I such that x prime. Yes, everything is x prime. Yeah, dt prime dx prime. Yeah, you're right. Thank you. Right, okay. So this is possible if we choose F3 inverse is the inverse of the matrix F3I. So imagine that you have chosen it this way, right? That then let's see what happens. So you have F3ij del phi j del t prime, right? So you get F3ij times F3 inverse jk, that becomes delta ik. So it basically converts this to F2i, right? And that exactly cancels this. It becomes minus half F2i, and that exactly cancels this. Is this clear? So the only danger here is F3 is singular. Okay, that's a very special case. You have not considered this. Okay, if F3 is singular, you have to do more work to do this, right? But let's assume that F3 is not singular, and then you can do this, right? So starting from any form of the metric where F3 is not singular, you can do this. Okay. And then phi j we can just get by integrating some arbitrary t naught to t dt prime minus half F3 inverse jk F2k. Right? All of this depends on t prime, of course. Okay, but it's something you can just integrate and calculate, right? As long as these are finite, this is a well-defined object. So this integral you do at fixed x prime, right? But just over t prime.
X prime dependence of phi is super arbitrary.
No, it's fixed by this because these depend on x prime.
We only know that the partial derivative of phi is
Yes, but this depends on x prime, right? So when you integrate, right, there is an x prime dependence that comes in. The initial condition, right? You can say, okay, at t naught, you can add an arbitrary x prime dependence, if that's what you mean. Yeah. So, yeah, you can add, but you cannot, the whole x prime dependence is not arbitrary, right? You can add a constant which is an arbitrary x prime dependent constant, right? But that doesn't depend on t prime. So that freedom you have, but otherwise it gets fixed. The t prime dependent part, the x prime dependence also gets fixed. Is that clear? Okay. So the net upshot of this analysis is that instead of starting with this general metric, we can start with the one where the half diagonal term is zero. Okay, we just now rename the coordinates t prime x prime as tx and work with this. That's a matrix inverse, yes. No, a matrix inverse, right? You think of F3 as a matrix, take the inverse of that. Right? Only then this F3ij and F3 inverse jk will combine to give you delta ik. Yes. Yeah. So here, for example, right? See, this fixes a t prime derivative, right? So when you write the solution, okay, you can add to this some arbitrary function f of x prime. It's not unique, yeah, right? But it's no longer a function of 4 variables. It's a non-uniqueness is a function of 3 variables, right? With a function of 3 variables, you cannot change another function of 4 variables. right? So you cannot just this kind of transformation you cannot make use of. Now to say that okay, we'll set this equal to 0, this equal to 1, f1 equal to 1, right? But we don't need to. Right now we are not going to try to set f1 equal to 1. Eventually we'll do it, but right now we'll keep f1 as it is. Is this point clear? Okay, so let me just write down the lesson from this analysis. Okay. Again, at this stage, we have said nothing about homogeneity and isotropy. It's just that by making a appropriate transformation of the x coordinate, we can get rid of the off diagonal terms. Is it clear? Now, if we are allowed to also make an arbitrary functional transformation on T here, we could have tried to get rid of the f1. Right? Take T to be an arbitrary function of x and T. Okay, that will try to get rid of the, you can try to use that to get rid of the f1, but we will not try to do that. You will see that later on, right? F1 will go away anyway. So all I'm saying is that we, to begin with, the general coordinate transformation had 4 independent functions. Right? Xi zeros are the because x can go to an arbitrary function of x naught can go to an arbitrary function of x prime and t prime, x prime and t prime, x1, x2, x3, each of those could go to arbitrary functions. So you had 4 functions to play with. And using those 4 functions, you might expect that you should be able to set 4 functions to 0 in the expression for the metric. Okay, like this is like choosing a gauge. Okay. What we have done is we have set 3 functions equal to 0, right? Not 4 functions. And the reason that you have not done it is because you are saying that T is something special, right? There is a cosmic time, okay, and we don't want to touch it at this stage. Yes? We don't want to make T into an arbitrary function of x prime and t prime. We can do that. We may be able to simplify the metric, but what we lose is that now the ability to impose homogeneity and isotropy becomes complicated because constant time slices are no longer the ones on which the universe is supposed to be homogeneous, right? Because they have changed the definition of the cosmic time. Yes.
We get rid of from the cross term.
Yes.
At the expense of adding some complicated terms to this dt square coefficient.
Yes, but you call that f1.
Now we are f1.
Yes. So this is a new f1, right? So this f1 is not the same as this f1. Okay, this f1 is whatever you get the dt square coefficient, the dt prime square coefficient, you get this was already there, then you have one from here, right? And also something from here. And all those have to be added. And similarly, f3 itself has changed, right? Because f3 is multiplied by these factors, right? That's what I'm calling the new f3. Okay, so let me write. These are not the same. These are not the same as the original. Not the same as the original f1, f3. Okay, so this will be our starting metric. And now we want to impose on this the restriction of homogeneity and isotropy. Okay. So with this, I'm now going to give the definition of what we mean by homogeneity and what we mean by isotropy, right? What is the formal definition of homogeneity? So homogeneity. So we'll call this space homogeneous if given any pair of points Px1 and Px2, two space-time points on the same time slice, right? I have taken the same t. Just check the notation I have used. And there should be an isometry. So let me explain the significance of this. Okay. Let's imagine that you have a constant time slice and 2 points x1 and x2 on that constant time slice. Now we want the physics around this point, the metric around these 2 points to look the same. Just like dx square plus dy square plus dz square had that property, right? The metric around any 2 points look the same, right? If you expand this in Taylor series, it looks the same. But suppose that they don't look the same. Okay. Does it mean that it's not homogeneous? And there the point is that the metric not looking the same doesn't necessarily mean that they are inequivalent. That there may be a coordinate transformation which makes the metric around x1 look the same as metric around x2. Right? So this is the more general definition of homogeneity, right? That if f is an isometry, that means the transformation f doesn't change the functional form of the metric. Right? But it takes x1 to x2. So what was x1 earlier, right, in this new coordinate system has become x2, right? And that shows that the metric around x2, right, is related to the metric around x1 by coordinate transformation. Is this logic clear? So if we had flat space time, right, then the f would have been just translation. F of tx1, the f of tx we will choose to be x prime plus x1 minus x2 or x2 minus x1, right? So that when you set x prime equal to x1, you will get x2. Right? So in flat space, this is implemented by simply choosing fi to be a translation. So flat space is obviously homogeneous in this sense, right? We have an isometry that does the job. But this is a more general definition of what we mean by isometry. What we mean by the space being homogeneous. Exactly. And this has to hold for every pair of points, right? I mean, if it fails for every one pair of points, then the space is not homogeneous, right? Because those 2 points are not equivalent. But doesn't mean that, okay, so the particular isometry that you have to choose may depend on the pair of points, right? That's true in flat space also, right? Suppose you have chosen x equal to a vector A or x equal to vector B, right? And you want to go from A to B. We have to translate by B minus A, right? So that isometry clearly depends on the initial points that you have chosen, right? Is a translation by B minus A. So for different pairs x1 and x2, we may have to choose different isometries. But once you have chosen the isometry, right, that acts on all points, right? And it's being an isometry means that the metric functional form of the metric should remain the same everywhere, right? Not just at those 2 points. Because you want the metric to look the same in a neighborhood of those 2 points, right? Not just at those 2 points. Right? You just don't want to make the metric equal. You have to make sure that the functional form of the metric in the neighborhood of one point is the same as the functional form in the neighborhood of other point after appropriate coordinate transformation. Is it clear? Everywhere. Yeah. Because around 2 points means you are extended, right? In the whole space. Think of the surface of a sphere, right? Given 2 points, right? The metric, once you have used the theta phi coordinate system, metric at those 2 points may not look the same. Yeah? Clearly, it depends on sine theta, right? So if theta equal to 0 and theta equal to pi by 2, the metric form is different. But what the sphere is still homogeneous because it is possible to make a change of coordinates in which the metric around one point may look the same as the metric around the other point. Compatibility, no, you can consider space time where it is not true. I mean, if you look at our space time, right? If you don't average, then it is not true, right? In solar system, the metric is different from, say, in outer space, right? And there is no coordinate transformation that you can find, but the metric in the solar system will be the same as the metric in the outer space, right? So it is not compatibility; it's mathematically, I mean, it's perfectly consistent with general coordinate invariance, yeah, general relativity. But this is a spatial form of the metric that we are choosing based on our understanding of the universe. In this case, the size of the neighborhood is infinite, right? Because we are demanding that it's an isometry, which means the functional form, right, doesn't change, right? However far you go, right? It's not the functional form looks identical in a small neighborhood. It's same everywhere, right? And usually, if the metric has some analyticity structure, right, then it follows that once you give the function in a small neighborhood, right? Once they agree in a small neighborhood, they'll agree everywhere. Right? Otherwise, you need some non-analyticity. Is it clear? Yes.
So those can be in any direction.
Yes, indeed. So infinitesimal ones means the x1 and x2 are closed, right? Then you need infinitesimal transformations because if you want to move a little, right, you expect that it should be infinitesimal transformation that relates them. Is it okay? Yeah, if you say do a Taylor series expand around theta, theta naught phi naught, and theta 1 phi 1. Right? Define say theta tilde is equal to theta minus theta naught, phi tilde equal to phi minus phi naught, and Taylor series expand the metric around in terms of theta tilde phi tilde. Right? And then do the same thing about theta 1 phi 1, right? Define another coordinate, say theta double tilde equal to theta minus theta 1, phi double tilde equal to phi minus phi 1, and write it as a function of theta tilde phi tilde. Those functional forms are not the same, right? The Taylor series expansions are different. Right? So if you just use this coordinate system, yeah, the metric will look different at those 2 points. Exactly, yeah. See, if I suppose I have d theta square over sine square theta d phi square, I make the coefficient of sine square theta d phi square multiply by some 1.2, some number. You will not think that you have lost any symmetry, right? If you just look at the metric. But you don't have the full isometry anymore, right? D theta square plus 1.2 times sin square theta d phi square, right, doesn't have the isometry that you had to begin with.
Then this isometry will be true for both of those points. G medium x1 would be equal to G dash x1, and same would be true for x2.
No, that's not what I'm saying. What I'm saying is the following, that let's imagine that you have x1 and x2. Okay? The form of the metric looks different around x1 and different around x2, right? They look different. Now, suppose you have an isometry, right, that takes the point x1 to x2. You apply that on isometry, right? It's a new coordinate system, right? In that coordinate system, the metric around x2, right, looks like what the metric was initially around x1, right? Because x1 has gone to x2, right? Functional form hasn't changed. So this particular coordinate system shows that the metric around x2 can be made to look like metric around x1. Right? If there is an isometry and if you can use it to go from one point to another point, right? That is good enough to show that metric around one point can be made to look like the metric around another point, right? This should be clear. You have 2 points x1, x2. You make this isometry, right? It takes you from x1 to x2, right? Now you want to study, so physical points are the same, right? It's just that the point, okay, imagine that you have a point P and Q. Okay. This was described by x1, this was described by x2. Now you make this isometry. In this new coordinate system, this point appears to have coordinate x2. Right? Okay. Same point, P. Okay. It appears to have coordinate x2. And the functional form of the metric remains the same. Right? So functional form of the metric around P in this new coordinate system looks like what the functional form was in the old coordinate system around Q. Right? That's the sense in which once you have an isometry that relates the 2 points, right, it is clear that the functional form of the metric around one point can be made to look like the functional form around another point by making that isometric transformation. Okay, so actually, I think it's important that you distinguish points from coordinates. Right? P and Q are fixed points. You have to make sure that the metric around P looks like the metric around Q. Right? And what you're saying is that you can, of course, always make a coordinate transformation where if the coordinate here was x1 and here was x2, right? It takes you from x1 to x2. Right? The coordinate here will be x2. But that is not good enough. You have to make sure that the metric looks the same, right? And isometry guarantees that. Right? Isometry guarantees that this gets a coordinate x2, right? And because the functional form of the metric hasn't changed, right? The metric around this point now it looks like what it was around this point in the old coordinate system. Yes, exactly. Right. So this homogeneity means that any 2 points in space should be connected by isometry.
Initially, we have P and Q with different coordinates x1 and x2. Now
Not defined coordinate system. In the x coordinate system, this had coordinate x1, this had coordinate x2.
now we want to do a coordinate transformation of the point.
No, everywhere. X prime, yes.
But now P coordinate x1, P will go to under this coordinate to x2.
Yeah.
But if that transformation is an isometry, whatever the form of metric about x2, which is the coordinate form, will be same as what we get.
Exactly. Exactly. Right. Because the functional form is the same. Is it clear? Okay, this is why isometries are important. Okay, if it's not clear, please ask, because this is the key point why you are making use of isometries, right? If you want to make the space look similar at different points, right, you need to discover isometries.
I don't understand is once we make this kind of a transformation, now the metric around P looks the same as the metric around Q, but after the transformation, the metric around Q must have changed, right? It will be something.
Yes, fine, but that is not a relevant point anymore. That is a point where f of x2 is, right? That may be some x3, right? It may look different, right? We are interested only p and q. See, x3 may be different. It may take it to a different coordinate system, right? But you want to know, understand that the metric around p looks the metric around same as the metric around q, right? And all you are saying is the original coordinate system, the metric around p was given by g mu nu around x1. Right? Now you make this isometric transformation. Right? Now the q has acquired, the p has acquired coordinate x2. Right? Now the metric around p will look like g mu nu of x2. But g mu nu has the same functional form, right? Okay. So what the metric here was earlier will now be the metric here. Right?
That was g mu of x2. After doing the coordinate transformation, it should be this way, right? It will be the same as
G mu nu.
So we can say g mu prime of x2.
Yeah, but it's not just enough to say that at x2 in the whole neighborhood, right? Because the functional form is the same, right? So it's not just that the metric values are equal, right? The functional form of the metric becomes the same. Yes, exactly. Yeah, but that is not that doesn't describe our universe. Yeah, yeah. So certainly you can talk about in a case where the whole space-time is isometric. Right? There's an arbitrary isometry not at constant time scales. But that's not what describes our universe. Right? That's why we are restricted to this particular class of isometries. Exactly. Yeah. Yeah, you can think of it that way, right?
But it's the thing is, it's on a constant time.
Yeah, exactly. T should be the same. Okay, these are isometries, but very special kind of isometries where the T is not changing. Oh, here saying that if 2 points are radiated by isometry, right, you can think of this as combination of infinitesimal transformations. Right? The Killing vectors generate infinitesimal transformations, right? So under under many infinitesimal transformation by Killing vector, you can go from one to the other.
Transformation is something like paper and shifted. It's different now, but it's still young.
Exactly. It will still be on the plane of the paper and the neighborhood looks the same, right? If the paper was crumpled, right, you could still shift it, but the neighborhood do not look the same. Okay, so now let me give the definition of isotropy. So pictorially, what it is saying is that imagine that you have a constant time slice, you have some arbitrary point here, and two other points at equal distance. Then there should be an isometry that leaves this point fixed and takes from this to this. See, if you didn't have the first condition, right, this point fixed, then homogeneity will imply this, right? Because there is always a transformation, isometry that takes you from any point to any other point, right? But this is an extra condition, right, that it has to take x1 to x2, but also leave x0 fixed. This is how rotation acts, right? Rotation around the point, right? You rotate keeping that point fixed. All three sets of points with this condition that x1 and x2 are equal geodesic distance. Okay, and here I should also say the geodesic distance. When I say this is in the 3D metric. Okay, in geodesics in the full space time, right, need not correspond to constant time slice. Right, so you forget about the time coordinate, right? Just think of F3i as a metric, three-dimensional space, right? That has its geodesics, right? And you measure it the distances by using those geodesics.
Generally, are there geodesics connecting any?
Well, at least if they're close by, there are geodesics that connect any two points, right? I think if the manifold has nice properties and the geodesics foliate everything, so it is possible probably to find geodesics that connect any two points, but I'm not completely sure about what happens in the general case, but nearby you can certainly do it. Right? You can think of from a given point the geodesic spread out everywhere in all directions, right? So any nearby point you can reach by a geodesic. Just like from here, you can draw a straight line to any other point, right?
Geodesic in the three-dimensional metric doesn't have to be a geodesic of full metric.
No. Yeah, you're not claiming that is a geodesic or a full metric. Yes. Well, it's finite that because that's all you can observe. We don't know that there is actually a boundary there. I mean, there is no evidence that there's a boundary in the observable universe. Right? We can only observe a finite distance because we are just receiving light from the beginning of the universe, right? And the light can only travel so much during the age of the universe. Right? That's what puts a limit on how far we can see.
That limit will be able to extract from this.
Yes, we will. I mean, cosmology will tell you how much that limit is. This 45 billion light years that I mentioned, that will come out from this calculation, this analysis. Because this is the only tool we have, right, at present. So you have to basically whatever I say better come out of this, right? Otherwise, it's I mean I cannot say anything. Is this clear? Yes. Diameter.
Yeah.
Yeah.
So that I said something like 45.
That's not the diameter, that's the radius. So we'll see how it happens, right? So it looks like I mean, light is traveling faster than light, right? But it's not that way. We'll see what it means. I mean, how that happens. Because yeah, see, that's a question you can certainly ask, right? I mean, if the universe is only 14 billion light years old, right? How could have light traveled 45 billion light years in that time? Yes.
What can you say about this definition in terms of the field?
So basically, this means that, so if you take again these two are infinitesimally close, x1 and x2, right? Then there is a killing vector field that vanishes at x0, right? And it takes x1 to x2. Right? X0 fixed means that killing vector field should vanish at x0. Any other question? Yeah. So if you look in the flat space case, right? This is insight from flat space, right? What does isotropy mean? That if you have isotropy around a given point, means that if you start with a given point x naught, right, and two points that are equal distance from x naught, there is a rotation that takes you from one to the other. Right? That's the sense that in whichever direction you look, the universe will look the same. Right? So in this notion of whichever direction we look, right, is this fact that you can choose x1 and x2 arbitrarily as long as they are the same distance, and they should look the same. Okay. Are there questions? Yes, yeah. But what we can show is that if the universe is homogeneous and if it's isotropic around any one point, it will be isotropic around any other point. Because the point is that if it's isotropic around any one point, right? Using homogeneity, you can bring any point to this point, right? And then it will be isotropic under that point. So isotropy, once the universe is homogeneous, it's enough to check isotropy around one point.
Why is it necessary for the x1 and x2 to be equal? Because they simply said it just this one point, and the other 2 points are the, say for example, the two distances. So also you can.
But think of flat space, right? Flat space is isotropic, that will agree, right? If you have a point, say origin, take that x naught, right? And take 2 points, right, which are not at equal distance, right? Can you think of an isometry that leaves the origin fixed and takes those 2 points to each other? See, by rotation, you can only take equal distant point, right? If you do translation, the origin moves, right? Then you violate the first condition, right? So the first condition is important, right? If you don't have the first condition, then homogeneity is enough. But keeping the extra point x naught fixed, if you want to move x1 to x2, they better be equal distance.
Last class you mentioned not homogeneous but
Yes, not homogeneous but isotropic is, yeah, if you take a sphere, right, and deform it, say ellipsoid, right? The surface of an ellipsoid is isotropic around the tip, right? But it's not homogeneous because the tip, the curvature at the tip is different from the curvature in the along the equator, for example, right? If it's an ellipsoid. So that's an example of a case where it's isotropic but not homogeneous. Well, it's still not the same, right? Because I mean, it's not that in a, however small the neighborhood is, by doing Taylor series expansion, you will see the difference. Isotropic. It's isotropic around. It is isotropic. Yeah, it's isotropic around that those 2 points. This point, right? Because if you rotate around this point, right, it looks the same. Ellipsoid looks the same, right? So in that sense, it's isotropic. Pardon? Yeah, only with respect to these 2 points, exactly. Yes. That is enough. Yeah, then it's isotropic around another point. Because then any other point can be brought to that point, right? Using the fact that it's homogeneous. Okay, so now let's get down to trying to find those isometries. So recall that we had this metric ds square as minus f1 e x dt square plus f3 ij ex dxi dxj. And let's suppose that isometric transformation is xi as some fi of dx. Okay, right now you are not talking about whether not specifying whether fi is isometry associated with homogeneity or isotropy, right? Some isometry. X prime. So you want that the matrix should look the same in terms of X prime. Right? That's the meaning of it's being isometric. But you can immediately see that that means that Fi cannot depend on T. Let's see dxi T is T prime, right? Because we are not touching T. So dxi is so if we calculate ds square, did I make a mistake? Okay. So we get cross terms, right? From here, right? So this has terms like 2f3ij plus other things if you don't right now. But the metric is supposed to look the same. Original metric has no dt dx term, right? G ti was 0. So it better be that G prime ti is 0. Right? But this says that G prime ti is not 0 unless del fi del t prime is set equal to 0. So conclusion, del fi del t prime is 0. Yeah. So you start with this and then you assume that the isometry is takes this form. Okay. You put it here and you get this form of metric. Exactly, because it's an isometry, it better look the same. The functional form should remain the same, right? So if G ti was 0, G prime ti also should be 0. Yeah, but you see the G prime ti is not 0, it has this term, right? So this is the advantage of making that work, doing that work that we did earlier, which is to use the freedom of coordinate transformation to set the ti component 0. Right? Once you have done that, right, then the isometries automatically are forced to have del fi del t prime equal to 0. Right? Which means that the transformations are time independent. Is this point clear? Yeah. So we got this conclusion. You agree? Okay. It basically comes from the fact that if you make a this isometric transformation, okay, the new metric has dt prime dx prime term, right? Which means g prime TL is not 0, right? But g prime TL is supposed to be the same as GTL because the functional form of the metric is not supposed to change, right? And GTL was 0. This metric has no GTL, right? So G prime TL must be 0, right? And G prime TL equal to 0 implies this, that F should be time independent. Okay. Now, if we didn't have this form of the metric, if the original metric itself has Ti component, then you couldn't have made this conclusion, right? So if you recall, the original metric doesn't have Ti component because initially, before we even discuss isometries, we had made use of the freedom of coordinate transformation to set the Ti component to 0, right? So that was useful because once you have chosen a coordinate system to make Ti component 0, then you see that the isometric transformation cannot depend on T. Yeah, so you are always talking about isometry that is keeping the time fixed, right? Because in cosmology, the homogeneity anisotropy only refers to the spatial slice. Exactly. So we have not committed ourselves to whether Fi is generating isotropy or homogeneity. That any isometry of the metric must have this property. Right? So both the isometry that generates homogeneity and the isometry that generates isotropy must have this property.
Something more general when we introduce that phi transformation with that cross terms also.
Yes.
The last piece. Over there, we got a condition on phi angle as an integral in terms of phi angle.
Yes.
So this is some special case of this.
Yeah. Now you are saying you start with 0 and you should end with 0, right? Yeah. So this thing was something non-zero in the earlier case. Now it is 0, right? Because you had started with 0.
So like just when we write the first metric.
Yes.
I can think of that like initially there was a very much more complicated metric with all sort of cross terms. I made some coordinate transformation and it was done by removing the
Cross terms, yes. And in that coordinate system, the isometric transformations have this simpler feature that the x prime can only depend on x and not on time. Right? If you had just insisted on using the original coordinate system, right, then it could depend on time. It is always possible. I mean, the proof that I gave F3 I took to be non-singular, right? But F3 being singular is a very non-generic case, right? If you have a generic matrix, its determinant is non-zero typically, right? So in the generic case, it is certainly possible. In a non-generic case, I didn't try to prove that it is possible. Yeah, I think people have proved, people have analyzed this. At least in the cosmological context, this is the most general metric that you can get. No, so what it is saying is that you don't have time varying isometry. In the cosmological context, right, all isometries must satisfy this, right? Once you have chosen your coordinate system that way. But in other cases, of course, you can have time varying isometry, right? I'm not saying that it's not possible to have time varying isometry, but in the cosmological context, isometric transformation should have this should satisfy this property. Is this clear? Okay, we also have other conditions when you compare this, right? Let me write them down. So F1 E x prime, sorry, F1 Tx Yes. Well, here we are saying that the cosmological metric has only those isometrics. Right? Time translation is not an isometric because our universe is changing with time. The only isometries that a cosmological metric has are the ones which are implement homogeneous and isotropic. Yes, in this case, we are not expecting any other isometry. Okay, is this clear? Okay, let me write one more step. So what is a new metric? Once you have implemented this, then the metric is f1 dx dt prime square plus f3 ij dx right? Because these terms went away. But if it's an isometry, then it should have the same form as the original metric with x replaced by x prime. T is the same, right? T is T prime. So x should be replaced by x prime in the original metric. Clear? This is prime. Yeah, thank you. Yeah, prime. No, no, because f doesn't depend on time. Sorry, del f. I think there are two kinds of f's. Maybe that is a confusion, right? Let me do something here. Put a bar here. This f1 and f3 appeared in the metric, right? These appeared in the transformation law. So this we put a bars. And that was the confusion. Oh, f with upper index and lower index. These are bars, right? So if it's an isometry, then this should be f1 t prime x dt prime square plus f3 ij t prime x dx prime I dx prime. Let me write KL yeah, so okay, here it should be x prime because this is at evaluated x prime t prime, right? So this metric, the original metric argument has to be changed to x prime t prime. So these are all x prime t prime. T prime is the same as t, but x prime is different. Here I can change t to t prime, right? Because t and t prime are the same, so there's no issue there. Okay. So now compare. So this tells us that f1 of t prime x is f1 of t prime x prime. And f3 ij of t prime x is F3 AL Is it clear? I'm just comparing these. Yes. So X should be thought of as a written in terms of X prime. Yeah, but T prime is always T. Yeah, so I can just replace T prime by T prime. Because replacing T by T prime is convenience, right? I can always do it if I want. So now look at the first term, this term. At fixed T prime, F1 at X and F1 at X prime equal to are the same. Right? So what does that tell us? It should be X independent because this is true for any pair X and X prime. Homogeneity guarantees that for any pair X and X prime, there is an isometry that takes you from X to X prime. Right? So this condition then is true for any pair X and X prime. That is important, right? That if it's true for only a pair particular points, right, that's not good enough. It does say that the function takes the same value at those 2 points. But because this is true for any pair X and X prime, we know that this is F should be X independent. So we conclude that F1 of T X prime is really F1 of T. The second observation, right, which is here, this can now be interpreted in purely 3-dimensional terms. Look at the left-hand side, right? What is this object, right? Physically, what does it say? What does it represent? Yes. Yeah. So this is like F prime 3ij. If you just think of this as a 3-dimensional space and make it, because these are independent of time anyway, right? You have seen. So just think of this as a coordinate transformation in 3 dimensions. And so this would have been in 3-dimensional terms F prime 3ij T prime X, right? T prime X prime, because you start with here and make a coordinate transform. So say F3 prime 3ij T prime X prime. What it is saying is that it is F3 KL T prime X prime. Right? So what is it saying physically? No, this is saying this is what it would have been if it had transformed like a matrix. But that would have been F3 prime of T prime X prime, right? That's the definition of a transformation. But it's saying F3 prime of T prime X prime is F3 of T prime X prime. This is why is it X prime? It should have been. So left hand, yeah, LHS. So this is saying that F3 prime KL T prime X prime. That's the LHS, right? That's the left hand side. This has the interpretation of F3 prime KL T prime X prime, right? That is the way it would have been transformed if you think of this as a general coordinate transformation in 3 dimensions. But what this identity is saying that this should be equal to F3 KL T prime X prime. This kind of relation we have seen earlier, right? What does it physically mean? That under a general coordinate transformation, the functional form remains the same, right? Which means that this can be thought of as an isometry of this three-dimensional metric, right? If you think of F3ij as a three-dimensional metric, forget about time now, right? Time is a fixed value, just a parameter. That for any fixed t, F3ij as a three-dimensional metric should have an isometry. Right? So a three-dimensional space that whose metric is F3ij is homogeneous and isotropic. Is that clear? Right? We started with four-dimensional space, impose some condition, right? But after doing all this manipulation, we are learning that if we think of a fixed time slice, then the three-dimensional metric is homogeneous and isotropic. Is this point clear?
Here you can see that the three-dimensional matrix which is given by F3i. Consider the transformations of Fi. How the metric is same.
So Fi's are isometries of the three-dimensional metric, right? Now isometries include transformations that implement homogeneity given any 2 points. They can be related by, there is an isometry that relates one to the other, and it also implements isotropy because given 3 points, right, 2 of which are equal distance from the third one, there is an isometry that takes you from the first to the second, right? So this means that the three-dimensional space, right? Now forget about time altogether. The three-dimensional space is homogeneous and isotropic.
Because the F bars can have any corresponding to
Yeah, F bars, see, F bars could correspond to either homogeneity. They are implementing the isometries of the cosmological metric, right? Which could be either homogeneity or isometry related isotropy, right? We now saw that F bars are independent of time. Okay, so once they are become independent of time, these transformations are as if we are making a general coordinate transformation in 3 dimensions, right? Now you forget about time altogether and just think of this as a 3-dimensional metric, and it's giving some property of this 3-dimensional metric, right? So what are those properties? It is telling us that there is a set of isometries that implement homogeneity in this 3-dimensional space, right? That given any 2 points, there is an isometry that relates the two. F bar includes those, right?
So what was the initial? So starting with general metrics and their properties. So are we? What are we assuming for F bars? F bars are transformation. You want to
Isotropic. F bars implement isotropy of the cosmological metric. We also demanded that the cosmological metric is homogeneous and isotropic, right? So F bars include some transformations which can take from any point to another point on the 3-dimensional slice, and it also includes some transformations which implement isotropy around a given point, right? So those F bars we can use now. Now we learn a new property that the F bars are actually time independent, right? So because they are time independent, we can just think of this as a general coordinate transformation in a 3-dimensional slice, right? Because there's a time dependence of these F bars. Now we work out the identities, right? And what we are saying is that this relation tells us that the F bars now generate isometries of this 3-dimensional space. Whatever isometries we started with. Exactly. Which is homogeneity and isotropy, right? On the 3-dimensional metric, right? But now this statement is purely in 3 dimensions on the 3-dimensional metric, right? We can forget about the time coordinate altogether, right? At fixed time, we have F3ij, which you think of as 3-dimensional metric, and that is homogeneous and isotropic. Is this clear? Okay. And this is important because these metrics are completely classified. Okay, because in 3 dimensions, once you have homogeneity and isotropy, right? Homogeneity gives you how many killing vectors? Infinitesimal homogeneity, right? You can move in any of the 3 directions, right? 3 killing vectors. Isotropy, rotation group in 3 dimensions, right? That's also 3 generators, right? So you have altogether 6 killing vectors. Okay. If you recall the maximal number of killing vectors that we can have, right? That formula, n into n plus 1 by 2. N into n plus 1 by 2. For n equal to 3, this is 6. Right? This is 6 for n equal to 3. Because the number of isometries that we have in this three-dimensional metric saturates this bound. Okay? So these are what are called maximal symmetric spaces. And there are only 3 of them, right? Which we'll write down next time. Okay, so because of this, now the cosmological metrics are completely classified, right? We can write down basically there will be 3 different forms of the cosmological metric that you can write down. Yes, T prime was always going to T, right? But what is important here is that this term vanishes. See, if you had kept the off diagonal term, right, then it will be harder to see. Of course, ultimately the physics is independent of the choice of coordinates, right? But if you had kept the off diagonal terms, then the fact that it can be thought of purely in 3-dimensional terms will be a little harder to see. Yes. Well, if you have more, right, it will be more constraining, right? And you have already saturated the maximum number, right? So at fixed time, you cannot have any other isometries. It better be dependent on these. See, this is a general result. The maximum number of killing vectors that you can have is this, right? And you have already seen that in 3 dimension, right? Based on the isometries that you have assumed, you have saturated the maximum number, right? So you cannot have any further symmetry of the metric. Right? I mean, okay, you can have further symmetry that involves time transition, right? You can say, okay, now it's also independent of time transition. Okay? That will be further symmetry, but that's not what we have in our universe. Right? Our universe doesn't have the time transition symmetry. Yeah, but the fact that homogeneity isotropy has saturated the number 6 means that it is not possible to have any other F bar. You are saying what you are saying is correct. If there is another isometry F bar, it would go through, right? But it will lead to a contradiction because that isometry will lead to a 7th killing vector, right? There is no 3-dimensional space with 7 killing vectors. 6 is the maximum. That there is a these are not there. The point is that the maximally symmetric spaces are all classified, and there are 3 of them, and those killing vectors will be these. Those spaces will be the 3 cosmological spaces, and they do have homogeneity and isotropy. Yeah, by definition, meaning, okay, the point is that's a saturation, right? You cannot have the number of killing vectors that is more than this number. Right? So what you are saying is that, okay, you don't demand cosmological space-time to be homogeneous and isotropic, right? You start with some other killing vectors. At the end, yes, you may get some other killing vectors, but if you have 6 of them, then you will be uniquely led to the 3 spaces that will be considering. Right? The 3-dimensional spaces with 6 killing vectors, right? There is no choice other than these. Yes, exactly. Yes, that follows. Yeah, but you assume that you have homogeneity and isotropy, right? If you don't assume that you have any isometry, right? Oh, whether they are homogeneous and yeah, true. I mean, if you say that you have 6 isometries, right? You don't care about whether they're homogeneous, whether they're implementing homogeneity and isotropy, right? Everything will go through, and you will be led to these three solutions. What he is saying is that let's imagine that we don't say it's homogeneous and isotropic, right? But some isometry. That imagine that you postulate that you have 6 isometries. You don't care what form they take. Right? Everything that you have said here will go through, right? And at the end, we will be left with a 3-dimensional space with 6 isometries. Right? And that will fix the form of the metric, right? And then we'll see that those isometries are implementing homogeneity and isotropy. But then you can ask why 6, right? I mean, that's a somewhat strange number to start with, right? So homogeneity and isotropy are more physical, right? We want these properties to hold, and that's how we start. But if for some magical reason you conclude that there are 6 isometries, then this is the only choice, right? These 3 will be the only choices. Okay, so I think tomorrow there is no class. So on Thursday again there will be class. Yes.
This calculation is telling me that isometries of this metric are the isometries of
the 3-dimensional metric. Yes.
Right.
And it is also telling you that F1 is independent of X. That's an extra information.
F1 is independent of X.
Yes.
And what about that number? Like, so FPIJ will have 6
isometries. Yes.
What is that telling me?
So the 6 Killing vector fields that saturates this bound, right? If you remember, I had told you that in n-dimensional space, the maximum number of Killing vectors you can have is this number. Okay. So for n equal to 3, this is 6, right? So these are called maximally symmetric spaces, right? The ones which have maximum number of Killing vectors, that is possible. And these spaces are all classified.
So the one we have this thing is corresponds to that space.
Exactly, right? So because these spaces are all classified, we can just read out what does these spaces are. There will be 3 different choices, right? And we write down all 3 different choices of this 3-dimensional metric.
So we will have some classification of some choices, some finite choices for the spaces to describe our treatments.
Exactly. Okay, so we'll continue then on Thursday.
Motivation to do all this studies on the 3+1. I mean, considering a space into the 3+1 spaces, keeping T as the one and T as the spacious.
Yes.
I mean, these as a motivation to proceed in this. And also, this each 3 case, you can consider it in the terms of the equivalence class in the mathematics. Because whatever we are doing in space, like, I mean, studying in with this point will in a way gives me whatever notion or whatever thing which I want to say in this point by a transition.
Yes, but the compatibility suggests that if this is not true, then there's something wrong with it. Right? But there's nothing wrong with it. There's nothing wrong with the theory. The fact that you have this isometry, that is a special property of our theory, right? which holds only over after the average over large scale. Right? So in that sense, I will not call it compatibility because it's not. It doesn't hold. It's not a theory you will break down. But even the fact that after taking the average, it happens this way, right, is part of experimental observation. Might not happen that way, right? I mean, we will see that there is an explanation of this, but that explanation is dynamic, right? not the dimension situation implies that it has to be this. In that sense, even after averaging, that compatibility did not demand that it will be. Not solid. I mean, asking those hard subjects. Yeah, yeah, in each ring it is homogeneous, but not homogeneous everywhere. Exactly. Yeah. Well, it is like norm because we are demanding the metric should look the same, but the metric essentially measures a norm, right? It is an arbitrary vector. So norm of an arbitrary vector should be present, right? That's what we are demanding. More than well, it's the same everywhere, right? Exactly. Yeah, exactly. It's not a property of the particular point. That, but isometry means that it's a norm you will use out everything. That you can certainly do it. Right? Just translation and notation. Right? Other spaces are not being described.